All right, so welcome to this morning session. My name is Dimitri Erhan. I'm from Google Brain. And I would like to start with the fact that the first oral of this session is received an award for Outstanding New Directions honorable mention. And I would like us to give a round of applause for this excellent work. So it's my pleasure to have Vincent here talk about scene representation networks, continuous 3D structure-aware neural scene representations. This will be a talk of about 12 minutes, and we will have opportunity for questions for about 3 minutes right after. So Vincent, thank you.
Do I have to do something? Or? OK, cool. Hi, I'm Vincent. I'm going to talk about scene representation networks, a continuous 3D structure-aware neural scene representation. Today, I'm going to show you how to get from a single observation of an object, meaning a single image, its camera pose, and its camera intrinsics, to a 3D neural scene representation that will enable us to do perfectly multi-view consistent null view synthesis and give us a full 3D shape reconstruction of the object. Let me formalize the problem first. We assume we're given a set of 3D scenes, and for each 3D scene, we're given a set of observations. And each observation is an image plus its camera pose and camera intrinsics. And for now, we're looking at very simple scenes, just a single object each. The question we're trying to answer now is, what can we learn about these underlying 3D scenes by looking at these 2D observations? And the vision is that at some point in the future, we can train neural networks just by watching videos that learn rich representations of our world. The model we're going to discuss is going to take as input a set of observations, process them, and then map them to re-renderings of these same observations. And that will allow us to train this model just with a 2D re-rendering loss. Specifically, the model is first going to map it to a neural scene representation, which is a feature representation that accumulates all the information of the observations in the scene, and then use a neural renderer to render out observations from arbitrary camera perspectives. So let me first convince you that this problem is not trivial. Let's build a simple 2D baseline. And our baseline is going to map an observation to a latent code with an encoder. In the latent space, we're going to concatenate an output pose, and then we're going to decode that into an image with a convolutional decoder. So the latent code could be seen as our neural scene representation, and the decoder plus the output pose is basically our neural renderer. So if you train this on ShapeNet on 2,500 cars with 50 observations each, this is what you get. And so clearly, this model failed to discover the 3D geometry of the underlying scenes. And we argue that to solve this problem, we will need a 3D inductive bias. Let's take a look at related work. We're going to classify it in terms of if it has a 3D inductive bias and if it can be trained self-supervised only with images. First, there's scene representation learning, such as neural scene representations and rendering. These models can generally be trained just with post images, but they generally lack 3D structure or a 3D inductive bias. Then there's 2D generative models. Similarly, these can be trained just with images, but they also don't have a notion of 3D structure. Then there's 3D computer vision, and that is usually concerned with reconstructing geometry and shape of a scene. And these often have a 3D structure, such as a voxel grid or a signed distance function, but they usually require explicit 3D supervision. And lastly, there's voxel-based representations, such as our own work, deep voxels or hologan. And these seem to check both boxes. However, voxel grids have their own problems. They're very memory inefficient. They scale cubically with the spatial resolution, and they don't parameterize scene surfaces smoothly. They discretize scenes, objects, and so on. And it turns out that generalization with these models is therefore hard. OK, we're now ready to talk about scene representation networks. And we're first going to talk about the neural scene representation itself. So let's consider a simple scene. We're going to have a gray background, which signifies free space. We have 3 objects, a circle, a square, and a triangle. And we have a coordinate system with a coordinate variable being x. We now propose to parameterize a scene as a function that maps xyz world coordinates to a feature representation of whatever is at these xyz world coordinates. So for instance, for all the x coordinates within the blue triangle, these should be mapped to a feature that says, I am a triangle, I am blue, and so on. All the coordinates within the red square should be mapped to something that says, I'm a square, I'm red, and so on. And maybe all the x coordinates in free space should be mapped to some feature representation of free space. So of course, that function is generally intractable. So that's why we argue we should parameterize it with a neural network. And that's what a scene representation network is. So a scene representation network is a neural network that maps XYZ world coordinates to a feature representation of whatever is at these XYZ world coordinates. Scene representation networks have a number of appealing properties. They clearly have a 3D inductive bias. They live in 3D. They can be sampled anywhere at arbitrary resolutions, and that's because it's a continuous function and it's defined on all of R3. They parameterize scene surfaces smoothly. They don't discretize space. And the memory they require doesn't scale with the spatial resolution, but instead it scales with the complexity of the scene. OK, so now we have parameterized our scene. How do we render it? We need a neural renderer in order to supervise it only with observations. Let's look at our simple scene again, and now we're going to place a camera in our scene. And now we want to render the scene from this camera perspective. The first step is we are going to have to find the intersections of each camera ray with the geometry of the scene. And remember, this isn't trivial because we don't have any explicit representation of the scene surfaces, such as points, but we only have this function that we can sample anywhere. So we're going to solve this problem by ray marching, by marching along each ray away from the camera until we hit a scene surface. So we could just pick a constant step size and be done with it, but that would be very inefficient, so can we do better? So let's march along this ray. We're going to start close to the camera at this coordinate x0, and we're first going to sample our scene representation at that coordinate, and that is going to retrieve a feature vector that describes the scene at that coordinate. We now propose to predict the step length from that feature vector and then advance along the ray according to that step length. So of course we can do that. The question is, why does that work? What does the feature vector possibly encode about the correct step length at that coordinate? And the answer is that there is a feasible step length for every coordinate in space, and that would be the distance to the closest surface in the scene. And I visualize this here with this black circle that just barely touches the surface of the red square. And for that specific choice of step length, this algorithm is called sphere tracing, and it's used in computer graphics to render signed distance functions. What we're doing here is, in fact, a generalization of sphere tracing. I'll refer you to the paper for the details. Just know that there is intuitively a function that we can recover from the scene and that maps to a feasible step length. So we're now going to iterate that algorithm for a fixed number of iterations. And the last iterate is going to be our intersection estimate. So now for each ray, we have an estimate of the intersection with scene geometry. Now we have to map each of these intersections to a color. So we're going to sample our scene representation a final time, retrieve the feature vector, and map it to a color with another neural network. So now we have everything in place. We have our neural scene representation. We have our neural renderer. We can supervise it just with observations. But so far, I've only told you you can train a single scene representation network with a single set of observations. So how do we generalize across a set of scenes? So let's say we have these cars here on the right-hand side. You could represent each of these scenes with the parameters of its scene representation network. But that's a very high-dimensional representation. We probably don't need as many parameters to parameterize these cars. So we're going to assume that these parameters live on a lower dimensional subspace, and we're going to represent each of the cars with a low-dimensional embedding. So now the question is, how do we get from the embedding vector to the parameters of the scene representation? And we propose to do that with another fully connected neural network, which is literally going to take the embedding and output directly the parameters of the respective scene representation. And this is known as a hypernetwork, a neural network that predicts the weight of another neural network and was proposed by Ha et al. In 2016. And intuitively, this is the thing that learns the priors over scene representations. This is the neural network that can learn cars have generally four wheels and they're symmetric and so on. OK, so I've skimmed over a bunch of details, like how to actually train this thing. I'll refer you to the paper for that because I'd love to discuss some results. Let's first look at reconstructing objects from the ShapeNet dataset. We're going to train on all the objects of the cars and the chairs classes, 50 observations per object. And then at test time, we're going to give it a single observation of an unseen object. So the top row is scene representation networks. The other rows are scene representation learning baselines. And as you can see, scene representation networks succeed at reconstructing the geometry of the cars and of the chairs and are perfectly multi-view consistent. So here's a few other samples. All of these were reconstructed from a single observation at test time. All these are unseen objects. Another very cool property of scene representation networks is that you can train them at one resolution, but then render at test time at a different resolution. So this model was trained at a resolution of 128 by 128. At test time, you can simply shoot more rays, because they're defined per ray, per XYZ coordinate, and render at a resolution of 512 by 512 without any retraining. Scene representation networks also generalize to completely unseen camera transformations. So this model has never seen a car up close. It also has never seen a car on its head. Yet it generalizes to these unseen camera transformations flawlessly. Compare that to a CNN baseline, which can absolutely not generalize to unseen camera poses. If you interpolate between the parameters of scene representation networks, that amounts to interpolating both the shape and the geometry of an object. And as you can see here, that will mean that the features of the objects transform from one to another smoothly. And also, you can see that each of the intermediates is also multi-view consistent. You can imagine that's also useful for rendering faces or other deformable objects like this one. So far, I've only shown you single object scenes. So this begs the question, can scene representation networks also parameterize more complex scenes, such as rooms? They can. I've trained this scene representation network on the rooms from the GQN paper, and I placed 2 ShapeNet cars in each of the rooms. And as you can see, that works just fine. This is a room from the training set, reconstructed from 50 observations. However, we have noticed that scene representation networks are not compositional. If you train them on rooms with 2 cars, they will generally not generalize to rooms with, for instance, 4 cars. However, we have been working on this, and we've extended scene representation network since, and we think we have something that works, so stay tuned for that. And that's at the end of my presentation. You can find me at poster 71. I'd like to thank my co-authors, Michael Zollhofer and Gordon Wettstein, who have been amazing mentors. And I'm also going to finish my PhD at the end of next year, or in the middle of next year, so reach out if you have research positions.
Thank you, Vincent, for this presentation. We'll now have time for a few questions. There's microphones on both sides of the room. Also, I would like to remind the spotlight presenters to please come here and maybe make a row, so that we're going to have spotlights right after the questions.
Hi, this is excellent work. I wanted to ask you about the neural renderer. In general, neural renderers have trouble with occlusions because that stuff is not differentiable. So did you notice that happening in your case?
I actually didn't catch the word. In general, neural renderers have trouble with what?
With occluded parts of an object, just because, you know, when these parts appear, disappear from view, this is not a differentiable phenomenon. And that was one question. The other one was, how about learning camera pose as well?
So in this case, I think that there is no discontinuity if objects get occluded or disoccluded, simply because of the ray marching operation. So because you march every single ray, and it's basically a signed distance field, I don't think I haven't observed any problems with that. And the second question was what?
How about learning the camera pose parameters as well? In your case, you assumed that they were known.
Yeah, that's true. I do assume camera parameters. I think this is an extremely exciting direction for future work. And this whole algorithm is differentiable with respect to the camera poses, so you can, in fact, backpropagate into the camera poses. So I think it's very interesting to extend this with a camera pose estimation algorithm, but I haven't done that yet.
Okay, thanks. Great work.
Hi. I'd like to ask how you would deal with specular lighting or reflections, which change based upon your viewpoint. So you can't just drop a ray and see what color is there.
I think that's a great question. So currently, for the record, I'm not dealing with this. Currently, the assumption is that scenes are perfectly diffuse. There's, I think, several ways how you could extend this. I mean, the brute force and maybe correct method would be to actually have secondary rays. After you hit a surface, generate secondary rays. Another, maybe more hacky method would be to also give the renderer the camera perspective, like the direction of the ray, which would help with learning view-dependent effects. And I think there's several ways how you could go about that. Thank you.
Hi. Great work. As I understood, everything was done with static images. Have you ever tested with real simple scene, but with real images?
We have. We have tested it with real images, but that isn't yet fully fleshed out. But there's nothing in principle that would be a hindrance here.
Thank you.
All right, let's thank the speaker again. Yes. All right, there's also an award which we now have, so there you go. Thanks again. All right, we're going to have the spotlights now. Oop. All good? All right. And for the spotlights, just a series of 5-minute presentations. There's no questions, but you can ask the questions to the authors afterwards. Thank you.
The other? Okay, so hi everyone. I'm Tolga Birdal, and I will be presenting this work on behalf of Leo Gibas, Qixin Huang, and Zhenshuo Liang. So a recent trend in optimizing maps, such as dense correspondences between objects or neural networks between pairs of domains, is to optimize them jointly. In many applications, there's a natural cycle consistency constraint that forces the composition along cycles to be identity maps. So a mapping graph is composed of a directed G and associated function family F over G. Each node U corresponds to a domain DU, and each edge UV in G corresponds to a mapping FUV from domain DU to DV. A cycle set is called cycle basis of some graph if all cycles in this graph can be composed by some cycles in basis set. Depending on the way to define the composition operator of cycles, there can be several manners to define cycle bases. So among them, the binary and fundamental cycle bases are the most common. In this paper, we propose a new so-called cycle consistency basis for our purpose. So here's the Venn diagram illustrating the relationship between three bases mentioned above. We proved that all fundamental cycle bases are cycle consistent and also provided a counterexample showing that some binary cycle bases are not cycle consistent. Next, we would talk about the cycle consistency basis in detail. A mapping graph G with function family F is called cycle consistent if the composition of F along each cycle G is identity. The number of cycles in a big graph can be exponentially large, so that it's impractical to check or enforce consistency of all cycles. Naturally, we want F to be consistent over all cycles of G whenever F is consistent over cycles in some basis B. So, unlike the binary bases, all fundamental bases are cycle consistent and can be generated by spanning tree of G efficiently. However, fundamental bases are not ideal since they usually contain many long cycles. Intuitively, long cycles are hard to be enforced consistent through the optimization algorithm. So to illustrate the principle of good cycle bases, let's consider a simple example. All functions over the network are defined to be a simple translation function with parameter Tij. We define such loss function to keep Tij close to the initial value while being consistent over cycle bases in C. By rewriting 1 into matrix form, we obtain a quadratic optimization problem. It has the well-known condition number kappa H. Recall that a smaller condition number leads to faster convergence rate of quadratic optimization. So we define kappa H as the condition number of cycle basis C. Then we focus on how to sample good bases given input graph G. It is noteworthy that the choice of cycle bases is abstracted from the specific function family, only depending on the graph G. Basically, the sample process can be divided into 3 steps. At the first step, we sample a superset C sup, which may contain excessive cycles and satisfy 2 properties. The cycles in C sup are kept short, but if the graph is sparse, some cycles would be included to address the issue of accumulative errors. The second step is to assign each cycle a proper weight. To this end, we solve a semi-definite program for optimizing weights. So the program enforces H close to an identity matrix and guarantees resulting cycles with non-zero weights indeed form a basis. After the first steps, we get a cycle basis with good condition number, but may still contain too many cycles. To solve this issue, in the last step, we utilize the importance sampling to trim out a part of cycles. Under mild assumptions, we proved in the paper that with high probability, the importance sampling process will not dramatically affect the weight sum and condition number of the resulting cycle basis. 2 experiments were performed to verify the algorithm we proposed. In the first experiment, the nodes represent different shapes, and each shape is connected to 25 randomly chosen shapes. Here we compute dense correspondences between different shapes using blended intrinsic maps. In another experiment, each node in the graph represents image objects viewed from similar camera poses. 25 camera poses are used, and we jointly learn the neural networks associated with each edge, as shown right. So in both experiments, our algorithm shows its superiority over previous ones by utilizing the cycle consistency in the graph. So for more details, please contact me later. Thank you.
Hello everyone, my name is Tang. Today I would like to present Cascade RPN, delving into high-quality reason proposal network with adaptive convolution. This is a joint work with Hin-Chun Chang, Phạm Xuân Trung, and Du Chang Dong. We consider the object detection problem. Given an image, we need to identify the object with a bounding box and class label. For high accuracy, object detection is formulated as a two-stage pipeline, where the first stage generates the reason proposals, and the second stage produces the final detection results. And our work focuses on improving the reason proposal quality at the first stage. Here is the architecture of RPN. An image is fed into a convolutional backbone followed by a shared head, classifier, and anchor regressor. There is an alignment rule in RPN design. Initially, we don't know where object is located in the image, and the common approach is to initialize the anchor grid uniformly over the image. And we need to set up the correspondence between the each anchor box and the feature points. And the correspondence is based on alignment. For example, the top left point should predict and refine the top left anchor. There has been studies focused on improving RPN, for example, iterative RPN. And in iterative RPN, a sibling anchor head is appended into the existing RPN. However, it has misalignment problem. As shown in the figure, at the second stage, the anchor is refined to be closer to the target object. However, it is not aligned with the feature points. Some recent advanced methods trying to use deformable convolution to perform features transformation and expect the transformation leading to alignment. However, the deformable convolution has been known to learn arbitrary transformation, and there is no constraint leading to alignment. To address the problem of misalignment in the previous work, we propose Cascade RPN with adaptive convolution to systematically ensure alignment through the RPN stages. Adaptive convolution is conceptually simple. The key idea is to adapt the sampling location at the feature space with the anchor box location as the image space. In standard convolution, the features are sampled at the regular grid by contiguous location. And in adaptive convolution, the regular grid is replaced by offset grid, which is guided by the anchor. And the offset can be decoupled into the center offset and shape offset, where the center represents the position alignment, and the shape of set represent the semantic scope alignment. We show the sampling locations of different convolution. Standard convolution sample at contiguous location. Dilated convolution trying to increase the dilation factor to enhance the semantic scope with unchanged computational cost. Deformable convolution learn arbitrary transformation, and only the adaptive convolution align the feature location with the anchor. We performed the experiments on COCO dataset, which is a standard dataset for object detection evaluation. Cascade RPN is compared to recent state-of-the-art method in recent proposal, and the results show that Cascade RPN consistently outperform the other method throughout the evaluation matrix. In particular, when compared with the second best method, which is guided GI-RPN, Cascade RPN achieved 2 to 3 point average recall improvement compared to the second best, with the comparable processing time. We visualize the recent proposal output of the first and the second state of Cascade RPN, and the results show that the proposal output of the second state is more accurate and cover larger of the object. Here is another example. Cascade RPN can be seamlessly integrated into the common two-state detector. Here we show the result with the fast and faster RCNN with different proposal method, and Cascade RPN showed better results. In summary, we have presented the Cascade RPN for ensure alignment between the sampling location of the feature space and the anchor of the image space to address the misalignment problem in the previous work. For further discussion, feel free to visit our poster at number 86. Thank you.
Hello, good morning. My name is Enrique Fita San Martin from Heidelberg University, and today I'm going to explain the probabilistic watershed, joint work with Sebastian Dandridge and Fred Hamprecht. So the first question that arises is, what do we do? And this is a question that even my girlfriend asked me once, but she's not from the field from computer science nor mathematics, so I make it simple and just answered that we count forest. And well, she laughed at me, but now I will explain why this answer is quite accurate. So in our scenario, we're going to have a graph, and we will have special nodes called seeds, and they are special because they have labels. And what we want to do is to assign a label to the rest of nodes which do not have. In order to do this, well, at the end we will obtain a partition over the nodes of the graph, in this case divided between red and blue nodes. To do this, we're going to use edge cost, which measures the similarity or affinity between the nodes of the graph, such that for a low cost, it implies a higher affinity. And finally, a forest in a graph is just a subgraph that without cycles and disconnected. And we are going to assume that this, this forest will separate always the seed nodes. So as you can see, a forest induces a segmentation or a partition in the nodes of the graph as we're interested. There are algorithms that use forests to compute these segmentations. For instance, the watershed is an algorithm that computes the minimum cost spanning forest. That is the one with minimum cost. But it ignores the rest of forest in the graph. And what we want to do is to take into account all the information of the other forest. In order to do this, we fix at a certain node, and we ask ourselves what is the probability of finding a forest where a certain node, let's call it Q, will be red or blue. In order to do this, we're going to count all the forests, in this case where Q is red. We'll count all these forests divided by all the possible forests, that is, where Q is red and Q is blue. And this is what we have called the probabilistic watershed. And that's why we count forests. But since we have forests with different costs, and we assume that the forests with low cost are more important, we define a Gibbs probability distribution that assigns a higher probability to the forest with low cost. And this Gibbs probability distribution, it depends on a parameter that somehow determines the entropy. So at the end, we count forests, but we just weight the forest by this probability. Now the question is, how do we actually count all these forests, since there are exponentially many forests as nodes in the graph? So, well, here there is the matrix tree theorem, which gives a closed formula to count the number of spanning trees in a graph. But since we are counting forests, we can make a small modification on this theorem and obtain the number of forests in the graph as we are interested to. By doing this, we have realized that the probabilistic water set is equivalent to the random walker by Grady, which answers the question that what is the probability of having a random walker starting in a certain node Q will reach first a certain seed, in this case the red seed, before the rest of seeds. And by this new interpretation of the random walker, we have been able to connect two different algorithms, the water set and the random walker. But actually, these two algorithms were related in a different manner in another paper in the so-called algorithm poor water set, which consider the water set as a limit of the random walker. When we now observe this power water set as from the point of view of counting forest, what we see is that this limit property is equivalent to minimize the entropy of our Gibbs distribution. So, and when our Gibbs distribution has a lower entropy, then the forest with lowest cost will be only taken into account. And that means that if we have only a unique minimum spanning forest, then we will obtain the minimum spanning, the water set forest. But if there are more than one, then we'll still be counting forests, but only the ones with minimum cost will be counted. So in summary, we have we have shown the equivalence of the random walker and the probabilistic water set. We have given a new interpretation to the power water set, and we show a technique to count the forest. Thank you very much, and we hope to see you in the poster 81, and have fun.
Good morning, everyone. I'm Zhu Yang from Institute of Information Engineering, Chinese Academy of Sciences. It's my honor to have this opportunity to introduce our work, Deep Mixed Model Clustering. Recently, we often find ourselves surrounded by complicated information coming from multiple modalities and across multiple platforms. Just like how we human beings sense the world by what we see, hear, and touch, embracing multimodal data provides the machine learning algorithms a zero way to understand the world. So to achieve higher performance, the majority of studies adopt a supervised setting under multiple modalities. So in this case, the supervision often comes from two aspects: the class labels and modality pairing information. So the latter contains alignment information for samples sparing different modalities yet representing the same instance. It could be helpful to find thematic correlation among the modalities and then align the features for each of them. But it's well known that the manual annotations is expensive and laborious, especially when the extra pairing information is involved. The labeling becomes even more complicated. So recent studies turn to an unsupervised setting under such scenarios, which works without data labels. However, traditional unsupervised multimodal learning still requires extra pairing information among modalities for feature alignment. Here we move a step further by considering a fully unsupervised setting where neither modality pairing information nor label annotations are provided. We call this mixed model data, and figure 1 here shows the difference between the traditional settings and our settings. So in this work, we focus on the mixed model clustering task. Take two mixed modalities, for example. The goal here is to learn unified representations for the modalities and then grouping the samples into K categories. So we believe here that the key problem is how to learn unified representations. A common choice is to learn a joint semantic space. However, it is hard to find a correlation among all of them when pairing information is not available, which makes the solution infeasible. In fact, we still have another choice, that is to learn the translation across the modalities. According to the previous work like CycleGAN, it is easy to obtain the cross-model mappings under the guidance of cycle consistency. Then the representation could be naturally aligned by transforming all the samples into a specific modality space. So correspondingly, we propose an adversarial learning framework to tackle this challenging task. It consists of 3 modules. First, for each modality, there is an autoencoder to obtain latent representations for samples. Then we build cross-model generators to learn mappings across those latent modality space with unpaired data. Meanwhile, we set discriminators to distinguish whether a sample is mapped from other modality spaces. So in modality-specific autoencoders, we use latent representations for each modality learned by single model data reconstruction. The cross-model mappings are constrained with cycle consistency to preserve correct model information. They could be viewed as generators which produce fake samples by transforming from other modalities. For each modality, the generator and the discriminator playing a minimax game that the discriminator D attempts to judge the real samples from fake ones, while generator G aims at fooling D by minimizing the difference between real and fake samples. When the game reaches its equilibrium, it is expected that the generator to be good at modality transformation, and the resulted transformations uncovering the correlation across 2 modalities enable us to build unified representations for all of the samples. So here we adopt the popular Westerstand adversarial laws for optimization. So putting all this together, we have the finally objective function. Okay, that's all of my presentation. If you are really interested in our work, please come and join us during the poster session. Thank you.
It looks like we're missing one spotlight presenter. So if you are one of these authors and you're here in the room, wave to me, run to the stage, or else we're going to finish early. So 1, 2, 3. All right. With that, we're going to end 1 minute early, and as opposed to 5 minutes late. So please enjoy the poster session. Thank you.